Right, we are going to start in 5 minutes. Can somebody write in chat saying whether the video and audio quality seems okay? There's something slightly weird that OBS shows me about the microphone, but I'm hoping that there's no actual issues. All right, works is good. Technically, we are starting in 3 minutes now. We will probably, I have like a whiteboard just in case, a virtual whiteboard just in case we need one. But today is gonna be a very practical coding stream that is gonna be mostly about Vulkan 1.3. So I'm hoping that we will not actually, we'll need like Visual Studio and stuff, but we won't need to diagram. But if we do need to diagram, I can grab the iPad. Before we begin, we can, we will not be able to get through everything because, we will see. So somebody asked me about Vulkan 1.3 and Niagara on the last Vulkan 1.3 stream. And I was like, yeah, there's not like a lot of interesting stuff that we can actually do because, the render path setup is simple in Niagara and things like that. So I don't know if we should do this. And then I tried to launch Niagara on my current system, and then it didn't launch. And it's like, okay, it became kind of obvious that there's some maintenance that we need to do on this project, but also I thought about this, and while both the render path and synchronization setup in Niagara is very simple, it is like a reasonable exercise to be able to do to try to convert from the pre-1.3 to 1.3 world. I haven't used any of the features that we're going to use today before, so it's also going to be a good exercise in sort of how intuitive are these new APIs for someone who knows how to use Vulkan, obviously, but haven't used them before. I haven't even read the specs that closely. It's been a while. So this is the plan today. We are going to fix the actual issues. The reason why, so I have switched to an AMD GPU a while back. For complex reasons, basically, I rebuilt my computer to use AMD CPU, and then I started having noise issues with my previous NVIDIA GPU, and then I tried to get a new NVIDIA GPU, and it was even worse because it had a coil whine that was incredibly distracting and annoying. And then I got an AMD GPU, and then that didn't work out, and then I got a different AMD GPU, and that did work out. So we're using a fairly low-end AMD GPU right now. I don't actually remember which one it is. Let's see. It's RX 6700 XT, which is like, I guess it's not low-end, but it's a mid-end GPU. It's not that fast. There are a few interesting consequences because of this. For example, we can't actually test mesh shader path, but we do get access to AMD tools, so that's cool. I don't know if we'll have time to look at them today, but also this means that it's a different driver, right? And I haven't really worked with that driver a whole lot, and so of course, we are using some feature that AMD doesn't support. Anyway, so because we are using a different GPU, we might need some fixes. So we're gonna fix whatever issues we find. Then we are gonna do a quick cleanup on during the Niagara series, we found a bunch of bugs, and most of them have been fixed, but we still have workarounds for some of them. And I know for a fact that one of these bugs that was an AMD specific bug is still there. even though I did report it a couple of years back. So we are going to report this bug again after verifying that like it works, that it still exists and things like that. And then we are going to actually update 1.3. We will have probably to update some dependent libraries. I'm going to try to make this as quick as possible because it's not really Vulkan specific. So then we are going to try to switch to dynamic rendering. Hopefully this will work. I have an interesting question which I don't have an answer to yet, so we're gonna find out. Like, is the CPU cost of beginning a render pass now larger because the driver has to assemble a bunch of stuff dynamically? And if it is larger, how much larger is it? So we're gonna figure that out, then we're gonna switch to synchronization 2. We might have to do sync validation, we'll see. And then we'll see how quickly we can go through this. We'll try to be reasonably rapid today. If we can look at the Radeon specific profiler, we will. If we don't have time for this, then we don't have time for this. This is more about the performance stuff, not really related to anything else. All right, so we are going to start. Oh, I will look at the chat kind of throughout the stream, and if questions come up, I will try to answer them. I cannot comment. I'm assuming you mean mesh shaders. I cannot comment on that question. Oh, this buffer. Yeah, I need to think about this. It's sort of, it's not really directly related, but there is some interesting intersection. It's an interesting idea. I need to think. There is this general after, so Niagara series is like what, 3 years old now or something like this. Let's see, November 2018, right? So it's actually closing on 4 years, which is a little nuts. Since then, meshlets came up in a new way, which is the Nanite project that Unreal team drove. It's a little bit of a different spin on this. It is more complex, much more complex to set up, but the payoff is larger. And like if you mean this buffer in that context, that might be interesting. I need to think about kind of what is practical to do on stream, what do I want to play with, things like this, so I don't know it. Anyway, so without further ado, let's start. So I have, the only thing I've done is I've opened the project in Visual Studio. Let me adjust the fonts a little bit. I've opened the project in Visual Studio 2022, which updated it, but otherwise we are working off the current GitHub version. So the first problem that I discovered, which is why I said, hey, actually we should just do the stream, is let me kill the sounds from the computer because I don't want them to be annoying. So the first problem that I discovered, hopefully it doesn't kill the mic. Does it kill the mic? It does not kill the mic, cool. So the first problem that I discovered is that, of course, on my current AMD GPU, we can't actually start because, hello. Oh, retry. Should studio assertion dialog, it's weird. So we can't actually run Niagara because we can't actually create the device. I will spare you the, like, I already looked into why this happens and I don't want to belabor this too much. But short story, when we create the device, we don't just create like a regular device. We ask for a whole lot of stuff. And we kind of have an implicit assumption that a lot of these features are supported, which they don't have to be. And we don't actually check this in a very rigorous way, like we try to create the device. If we can't create the device, tough luck, right? And some of these features we actually have to have. And some of these we can survive without any issues. And the issue is my AMD GPU doesn't support one of them. So I wanted to go through the list of the features and remove the ones that we don't actually use. Now there is a little bit of a problem in general here, which is that I don't have my NVIDIA GPU to test anymore. And so any changes we make today, we need to be careful. Like, we have two render paths, one that uses mesh shaders, one doesn't. We can only test the one that doesn't today. So do we break the one that does? Who knows? So I'm going to be a little bit careful. But let's just go through these features one by one, because it's going to be a good overview of like what we use, what we don't use. So multi-draw indirect, we do use it because we dispatch a large render, like we dispatch a series of draw calls with one command. We do use statistics query to compute the number of triangles that we actually rendered. We could live without this feature, but I think probably all GPUs support it, so like it doesn't matter. We do use 16-bit math in the shaders. 16-bit math is a... I don't want to go into too many details because like the stream can go on forever if I explain everything. But we do use some 16-bit stuff. I guess our vertex has 16-bit flows, which I forgot about. But when we use the mesh-led path, we use 8-bit, and somewhere we use 16-bit integers. So like in general, we are trying to rely on 8 and sometimes 16-bit 16-bit values in the shaders. In 64, we don't... In 64, I didn't think we use in the shaders. Unless... No, ballot is UVec4. This thing is UAnt. There might have been a point where we used ballot and it required... Oh, I don't have the extension to highlight GLSL shader code. That's a shame. I don't want to set it up right now. So let's just live without highlighting. I don't know why we added UINT 64. I want to say we never use 64-bit integers in the shaders. Let's check. Because again, I don't wanna break things if I don't have to break things. Oh, that makes sense. Right. When we were experimenting with GPU buffer pointers, we had to use 64-bit integers because that's what they are. Vulkan 1.3 requires device address now, so I think let's just leave it alone. Like, this is not... I know exactly which one, which flag is the problem because I already looked. So anyway, we do use 16-bit integers, as I mentioned a little bit, and we use it in the mesh shader path, so I will keep that. We do need this feature because, again, we do GPU side calling, so like that needs to work. So we do use 8-bit integers in the mesh shader path, I believe. Yeah, our mesh lets use 8-bit integers to pack data more tightly. Technically, we could... Why does it keep... Oh, because this tab is temporary. Great, okay. So we can technically make this conditional on whether we use mesh shaders or not, but like I don't kind of want to. We do use storage buffer. These are two weird flags because one seems to subsume the other. So anyway, so this is our actual problem. This is the feature that is not supported on my AMD drivers. The good news is we don't actually, so this refers to the ability to use 8-bit constants, 8-bit integers in push constants. We do use push constants, but we always use 32-bit push constants, I believe. I think the reason why this flag is there is that when we were going through this like 4 years ago, whatever, at some point I said, hey, I just want to rely on 16 and 8-bit integers like everywhere. I don't want to think about this. So I'm just going to enable everything because like, why not? And NVIDIA GPU supported this at the time. Of course, AMD GPU doesn't. So we are gonna remove that. So we do use float 16. We do use int 8 in general in the shaders in a few places, so I'm gonna keep all of the other stuff. I forget if we actually switch to scalar block layout, but again, like drivers should support it, no problem. So I think this should actually be sufficient to run this. Let's see. It is not. Damn it. Hold on. Oh, okay, cool. Oh, no, huh. Wait, what? Hold on. All right, this is going to be worse than I thought. Oh, yes, this was a different problem, right? So we got past our first issue, which is we were asking the driver a feature that it doesn't have. Then the other thing that happened is we ran this code last time, like years ago, right? We did 1.2, what was it, like a year or two ago? The validation layers improve every time, and I'm running off the latest Vulkan SDK right now. So we are also testing our code versus against the latest version of the validation layers, which means that there are some problems that validation layers now report that they haven't reported before. So here, I don't know if you can read this, but now you can. The validation layers are telling us that we are requesting the capability draw parameters. Draw parameters refers to the shader feature where you can get the ID of the draw. And this is really critical for us because we are drawing a lot of objects in a single draw call. So we need the draw ID to be able to look up their transforms. So it says we haven't asked we haven't said that we require the device to support this. So this is like an inverse problem where the thing we just removed, from this was like we asked for a feature, but we didn't actually use it, so we didn't need it. This problem is the reverse, which is we are not asking for a feature, but we're actually using it. It is a core feature somewhere. Yeah, so it is a core feature in actually 1.1. We were using this feature from the very beginning. I think the issue was the validation layer didn't check correctly that the feature is enabled. And so in theory, our code could have misbehaved on some hardware, some drivers, right? Because we weren't actually correctly adhering to the Vulkan spec. Stuff like this is really, really easy to accidentally miss. And so whenever validation layers improve, it is common for them to discover bugs that always were there in existing programs. I don't know if this is it. I forget. Oh. This is not it yet. Let's see. Oh, we are... What? Hold on. Oh, we are asking to upload an empty buffer. What? Oh, I see. Okay. Now that I think about this, we never checked if our code works, if our code is able to render no meshes. We were so focused on rendering like a very large volume of meshes that we never checked if we can render nothing. It's not actually super important. I don't want to spend too much time on this, but right now this doesn't work because it wants to select an actual mesh. All right, you know what? So you can't upload apparently an empty buffer. We don't really need to do this. So let me just do this. The issue is we don't have good error handling. And I don't want to handle this. All right, so I think this hopefully is the last thing. Okay, all right. So we fixed all of the bugs, or we fixed all of the bugs that the validation layers told us about. We can now actually render everything. So quick reminder, so we're running on AMD GPU, which means we aren't using the mesh shaders because mesh shaders use an NVIDIA specific extension, so mesh shading is off. We render a whole lot of objects. We render a bunch of triangles. I hear my GPU fan spinning up. We have occlusion calling and level of detail, so we can toggle both. When I toggle occlusion calling, nothing on screen changes, which makes sense. But the number of triangles that you can see in the title bar goes from 14 million to 22 million. And then we have level of detail, which again is enabled if we, so this disabling level of detail increases number of triangles from 14 to 18 million. So it's not, our curve is not very aggressive, I guess. Yeah, and so like we render, oh, and we have some shortcut I forgot about. Is it this one? Yeah, we have a shortcut. The way occlusion calling works is we are rendering the depth buffer, then we are taking the depth buffer that we have rendered, we downsample it, we build a pyramid, and then we use that pyramid to reject, to check visibility for objects. And the way this works has been explained at some previous stream, like it uses 2 passes to call the geometry and things like that. So all of the other stuff appears to work. So this is our first problem finished. Let's see. Yeah, so nanite is like a giant topic that, you know, recreating nanite outside of Unreal could be an interesting exercise. I don't know that I'm ready for it. It's a bunch of work. It's, you know, doing this on stream, I don't know. We'll see. All right. Niagara should probably run on Linux. I mean, I never tried. I don't think so. We use GLFW, I think, to create the window. There's no CMake support. There's actually a pull request that I really should merge that somebody contributed, which adds CMake. And so with that, maybe it just runs. Maybe it doesn't run, but like I think if it doesn't run, it runs for some stupid reason that is easy to fix. So like I don't think I don't use Linux outside of the Windows subsystem for Linux, so I can't actually validate this. But I don't think this should be a problem. I don't think we have anything specific. I haven't tested tessellation with mesh shaders. Tessellation is difficult to implement. Tessellation is like some variants of tessellation should be easy to implement with mesh shaders, but a full replacement of the existing pipeline is non-trivial. Anyway, so let us commit what we have so far. We have terrible Windows new lines everywhere, but so this should be, I think it's day 16, even though it's been 4 years. Fix validation, errors and support, recent AMD drivers. It's kind of interesting that this AMD thing was a problem because I did test on AMD at some point in the past. And so the fact that the drivers don't expose 8-bit push constants is weird because they used to. But maybe, well, or maybe what happened is the drivers didn't actually check. Like you requested storage push constant 8, drivers didn't check this boolean but didn't support, like, so I don't know what fully happened there. It's a little surprising that this is a problem, because this code used to run on AMD hardware at some point. It just stopped, but hey, now it does again. Cool. All right, so now that this is out of the way, let's quickly go through the bug list. I just want to clean out the workarounds that we had. The biggest set of workarounds that we had was, so, oh, there's only one. Okay, we have this debug callback. So there's two workarounds, I guess. So we have this debug callback that filters out validation messages. I guess there was a bug that we must have filed like ages ago, 2020. It's not actually ages, it's only 2 years. And this has been since fixed. And so if you use, and because we are updating to Vulkan 1.3, we are going to stop supporting Vulkan 1.2 because, you know, life is short. Any 1.3 SDK should hopefully not have this problem. Let's check if this is true. It's interesting that the startup is a little, I guess I'm running in debug with the debugger attached. So I'm wondering what takes time there. 1, 2, okay. Oh, I guess we're also, so we still haven't hooked up the pipeline cache, so we're actually compiling all of the shaders from scratch, which can be fast. Anyway, we won't worry about these small details for now. Okay, so this, we don't need this workaround anymore. So the other big thing that I was hoping would be fixed was this. And I know it's not fixed because I already checked. So the way, so the way our calling works, so we do GPU side calling, which means the GPU takes the meshes that we want to render and then actually assembles a draw call list for the meshes, or it marks the meshes that are visible. And then I guess, do we have another? It's been so long, I don't even remember. Let's see. So we have this, yeah, okay. So we have this shader that we're calling the call shader. What it does is it does visibility checks for the mesh. And then it can do occlusion calling. And then if the mesh is visible, it appends the mesh. It appends the draw command to draw the mesh to like the global list of draw commands, and then the mesh gets drawn using indirect rendering. This shader runs twice in the frame. This is what this late thing is for. The reason why it runs twice is that to support occlusion calling without any lag, so there's like some occlusion calling schemes that have a single frame lag where the results of occlusion get used on the next frame. And this means that if you have a sudden camera turn, you may not see the object for one frame, even though you should be seeing this object for one frame. You can see this in almost every game that is based on Unreal Engine. Whenever you see like there's a camera turn and there's a sudden flash of white very, very briefly, like this is what it is. An object is not rendered for a frame because the occlusion calling system has a 1 frame delay. Our occlusion calling system doesn't have this. To make it work, we call the objects, we render the objects that were visible last frame because the assumption is that they're still visible. This gets us a depth buffer that is pretty complete. It's not 100% complete, but it's like almost complete. Then we take this depth buffer, we downsample it, and we then call the objects again. The condition for the second pass is like this. If we haven't drawn an object yet in this frame, like if it was not visible last frame, but if it is visible now, and the way we know this is by doing the occlusion calling, then we need to render it because this fixes this 1 frame problem. So because of this, the shader runs twice. And I hope there's no bugs in the actual logic here, like it's been a while, so we can just see if the object is visible, and yeah, Yeah, so see, in the first pass, we render the object. So we render twice, late is false on the first pass and true on the second pass. The first pass, we say if we're in the first pass, then we only render if the object was visible last frame. So draw visibility tracks the visibility across frames. Then in the second pass, we do the occlusion calling. This is the occlusion test. And in the second pass, we fill this buffer for the next frame. And we output the command if we are in the first pass, if the object is visible, which means it was visible in the first frame. Or if we are in the second pass and we know that the visibility status from the last frame was 0. So essentially, this condition makes sure that we don't render objects twice, once in the first pass, once in the second pass. Anyway, so this logic seems sound. You know, we've written this like years ago. It seems to hold up. This code seems to work. It worked on NVIDIA. Now, there is this workaround. So when I wrote this code first, I was like, okay, cool. This is an opportunity to use Vulkan specialization constants. The way this works is you add this constant, and then you can compile two versions of the shader, one with the constant false, one with the constant true. And then you use two different shaders in two different passes. Unfortunately, on AMD, what happened years ago is that this broke the code. It is difficult to know how it broke the code exactly. I think my suspicion was that the driver always treats this boolean as false. As in, instead of specialization constant actually flipping the behavior, it's always as if you are doing this early calling pass, which also means you never fill the visibility buffer, which means you draw nothing. And I think I updated the drivers yesterday. Unless that fixed this, I think this might still be broken. So let's check. Yep. We are rendering a grand total of 0 triangles. Now, you could suspect that this is a bug in the code, but this did work on NVIDIA. And I think this did work on Intel, if I recall correctly, but it's been a while. So this comment still is true. The way we work around this problem is that we use a single shader, but we get the data. We get this boolean from a constant buffer instead of like a specialization constant, which can make the shader a little slower because the if the specialization constant works correctly, then for example the first pass, the first shader run through, this entire like code can be removed from the shader binary that runs on the GPU, which may, for example, increase the occupancy, like the efficiency essentially of the shader. So it felt like, you know, it feels like an optimization that might help, but unfortunately on AMD we can't even check if this optimization helps or not because this optimization is broken, right? Now, let's double check that we are defining the specialization constant correctly in the shader. I don't know that this would be here. So let's double check that we got the syntax right. Yeah, I mean, we can try using an integer. This is something I haven't tried yet. So let's try, maybe it's just a problem with booleans for some reason. Specialization constants can be integers or booleans. But then the issue is, hold on. So let's try this. Nothing. So it's hard to diagnose this problem, right? Like I suspect it's a driver bug. It's hard to know what exactly happens here because it's unlikely that specialization constants are outright broken in AMD. It could be that the specific shader, something specifically in the shader breaks it. Like, I don't know, maybe this specific thing, like this specific code pattern breaks the shader in case this is a specialization constant. Like this bug could be very specific. This could also be an application bug. I suspect it's not an application bug because again, there's no validation errors and this code does work on NVIDIA and I'm pretty sure it works on Intel without the workaround, but it is hard to know, right? Maybe we aren't respecting some specific rule somewhere in the spec, you know. We should double check, which like I'm pretty sure is right, that we are correctly sort of passing all the specialization data. So as I mentioned, we create the compute, we compile the shader twice effectively, or we compile the PSO twice, once with the false value assigned to this constant and once with the true. We can check that we seem to be filling this specialization info correctly. I don't know if this is true. What? But we can check. But it's a little difficult to mess it up, especially in a way that somehow breaks only on AMD. There is a single entry that says constant ID 0, which is written in the shader. Offset and size refer to the location in the map. You may have noticed that we're using a boolean in GLSL, but the boolean in Vulkan maps to a 32-bit integer that can be 0 or 1 on the C side. So this should be fine. There's a total of 4 bytes that should be in this buffer. And if I were to look at this buffer, oh god. And then it's 0. And then on the second run, it's 1. So I don't know. It could be that the driver like caches this in some weird way. What if we swap the order? Nah. Anyway, so this seems, to me, it seems like a driver bug. I reported this bug years ago, but I guess the bug fell through. Things like that happen. So we're going to report this bug again right now. Hold on, let me go. Okay. Let me look at the chat quickly. So what, I mean, when we tested mesh shaders on NVIDIA GPU, we saw an uplift in performance compared to not doing the fine-grained culling that you can do. You can implement this whole scheme in a different way where you generate a dynamic index buffer. We haven't tested this. It's more involved. It requires more memory bandwidth. It requires an extra pass. Async compute is difficult to set up in that fashion because you have to overlap it with something, but like you can do this, right? It's much more involved, which is why we haven't tried. So, spec constants are a feature that, damn it, it's like, it's so good. You can, if every backend has specialization constants, you can, last time I talked, for people who were at the last stream, I talked about the fact that a lot of pins, a lot of shader permutations in projects that have a combinatorial explosion of them are actually there for performance. Like you can enable the feature and it's going to render just fine. It's just that, you know, the performance will suffer a bit. Specialization constants are great for this in theory because you can essentially have a bunch of these booleans and then you can set them to true by default. Oh, I wonder if we set this to true by default actually, what happens? Nah, I don't know. I don't know what's going on here. So like ostensibly, so you set them all to true by default, and then you compile one PSO, and then you render everything with it, and then you just toggle these bits, and then in background you compile specialized versions of the shader, and then when the PSO is ready, you switch to that for some draw calls, and all of this can be super transparent to a lot of the systems in the engine. So in theory, they're great. In practice, they're supported sparsely, I should say, as in like they're supported on Vulkan. But if your game is portable, you may want to target DX12 or Metal. Metal has something like both. I forget what the status of this is on these other two backends. I wasn't paying. I think Metal has them now, and I forget about DX12. But like in theory, they're a great feature. I mean, they happen to be broken in this specific case. I doubt again, like if specialization constants were broken on AMD drivers, this would have been fixed long time ago. There's conformance test for this. I think what happens here is some specific interaction between the fact that this is a specialization constant with something else. Or it could again be a bug in our application. We just don't have a way of knowing that. So, so let me commit, remove the workaround for 1-2 days. So we don't need this anymore. And we do have this bug. And by the way, the reason why I know that this MD bug exists is that we were tracking the bugs that we have encountered. There were only 2 bugs that we haven't confirmed as fixed. One was this one, which, you know, still broken. The other one was this, which is funny because I reproduced this bug on a Microsoft Surface, which I don't own anymore, and so I can't validate this bug. But if you click this link, it goes to an Intel community forum, which doesn't, like, I think Intel has changed their forum structure, so this link is effectively dead now. And I tried to find this bug on this forum and I couldn't, and so maybe they have just wiped the whole thing. And so I don't know. This was like a bug that has existed for several years. And I don't know what the current status of this bug is. This was like not a bug with Niagara. It's like any Vulkan application doesn't function when you, there was some specific process, I forget. It's like, I don't remember the details. It was something about switching, like I don't think it was just enough to plug the display in. But maybe it's like if you start the system, plug the display, then start the Vulkan application. Or maybe your Vulkan application is currently running. Right, I think maybe it was that your application is currently running, then you plug the display, the swap chain gets out of date, so you have to recreate it, and the recreation crashes the driver. I forget. But anyway, so we don't know. Let's mark this as this. Is this actually going to render like this? No, it's gonna render beautifully. Okay, let's flag this as like, I don't know what the hell happened here. I can't reproduce this because I don't have an Intel system anymore. So like, maybe it's still a problem. Who knows? I don't even have an Intel CPU. Anyway, so this is still a bug. I want to update the repro instructions so that they're off like latest. What's the line number? Change 0 to 1 on line 10. So, all right, so let me report this and then we're actually going to start doing 1.3. There's no way that we are going to get to RGP. This this stuff is taking. So this is done, except that I want to report the bug. So I've been told that the way you can report the bug is here. Alright, so let's see. So this is clearly a problem in the driver. The affected application is Niagara. Seriously, so it wants me to select, okay, another application, Niagara. I don't even know. So this is the only way to, as far as I know, to report bugs to AMD using like semi-official channels. So we are gonna do that. Changes, C shaders, draw, Qualcomm, GLSL, line 10. Change 0 to 1. Change 0 to 1. Start the application. Passing path to data kitten obj. Okay. The application renders nothing, whereas without disabling the workaround, it correctly renders kittens. This seems to be a bug with that shader's interaction with Vulkan's specialization constants feature. All right. I don't know what else to say here, so I'm just gonna do that. Hopefully this doesn't break the stream, the fact that I'm reporting a bug via this tool. All right. So we submitted the bug report again, like hopefully that actually helps, we'll see. Yeah, you can have multiple GPUs on your system, it works fine usually. So like in theory, you could actually have an Intel CPU with an integrated graphics in your desktop, plus 2 GPUs, AMD and NVIDIA. My current system is built, I do little GPU work these days, and my current system is built around minimizing the noise to the extent possible, which is why I'm using a medium-end GPU instead of high-end GPU. I also don't really play games on PC anymore, so. But yeah, like if you are doing graphics development seriously, then you should probably have a 3 GPU setup. With Intel Arc, you may be able to pull off 3 GPUs, 3 discrete GPUs from 3 vendors in one system, which is actually probably a good idea because you probably want an AMD CPU if you are a developer, because it has more cores and things like that. So anyway, yeah, so you can pre-process the shader using SPIR-VOpt. That is correct. I don't. We technically do compile it. Once. Yeah, it's plausible. I don't want to do this But yeah, you're right. It can be a workaround. Anyway, let's start doing actual Vulkan 1.3 stuff, because we are done with everything else. We reported the bug. Oh, I guess we haven't. I don't want to update like all dependencies. So fast obj doesn't matter. GLFW, GLM doesn't matter. The only thing I want to update is Vulk, just in case, because I don't know that the version that we are using supports 1.3. Probably doesn't. How do I do this again? Like this, right? Okay. I think this is it actually. All right. So so we updated Vulk, which is the loader library we use to the latest version. So that was quick and easy. We could update other projects, other dependents. I don't know that we need to. GLFW in theory shouldn't matter much. We are using a fairly old version. Let's just try to update things that we can try to update, and then if things just work, we are just gonna yes. The problem with GLFW is we are adding sources. Like at some point we're gonna switch to CMake, and these problems will not concern us. This is the wrong Niagara. All right. But simply this is what it was complaining about. If this doesn't just work, we're just gonna, the only thing I knew I had to update. Oh, that was a mistake, clearly. WL is Wayland, right? Oh, it might have been this file actually. Hold on, I shouldn't have done this. All right, so let's try this one more time. Yeah, it might be okay. So we need this, and we probably need this. Okay, almost. GLFW connect now. Oh, maybe this is just okay. Hold on. Okay. All right. If we use CMake, this would not require work. Okay. And then finally. All right. Okay, so is that how we do it now? Hold on. Some things were not meant to be. We're only gonna update half of the dependent libraries that we use today. Because when we update GLM, something changes. They probably change some conventions for some matrix functions, which feels rude, but okay. Okay. All right, so the main thing we needed to update was Vulk, because Vulk is actually updating Vulk would actually be required for 1.3 to be used probably. And yeah, there's a CMake PR, but like I don't want to merge APR with CMake right now, because I don't want to. The last thing I want to do is debug CMake on the stream. Okay, anyway, so we upgraded some libraries that we could easily upgrade. We didn't upgrade GLM, which probably there is just a single call somewhere that changed its semantics, but we will not deal with that. And we will not update Mesh Optimizer either, because it's used in the meshlet path that we can't test. And if we can't test something, I don't want to update it. So let's actually go to 1.3. It's been almost an hour, but all of the preparatory work is done. So the first thing we need to do is we need to actually switch to 1.3. So when we create the device somewhere, now when we create the instance, I guess. Okay, so when we pick the physical device, we need to pick the device that supports 1.3. When we create the instance, we need to create a 1.3 instance. And that should in theory be sufficient. Now let's double check that it is. So there is this chain of structs that we use when we create the device. Okay, so I have GitHub Copilot enabled, and it sometimes does magical things. In this specific case, it did a thing that is pretty magical, because it's almost what I wanted to write. With one exception, there should be 3. Okay. Oh no, the next channel is, okay, hold on. So there's this thing, which is the features that we are going to use. We are going to enable some of them. So like we want to use dynamic rendering, we want to use synchronization too. So let's just do that. It would be funny if the driver that we are using doesn't have support for some of the stuff that we want to do today, but I guess, okay. And then there's this awkward process whereby you chain the structs together so that the driver knows about all of them. So like in theory, what we have done now is that we are only supporting GPUs that expose Vulkan 1.3 now. We are creating the instance with Vulkan 1.3, so we are requiring Vulkan 1.3 runtime. And we are saying that we want to use dynamic rendering and synchronization too, both of which should be required features for 1.3. So the fact that we are requesting them doesn't mean that we kind of increase our requirements beyond baseline 1.3, but this does mean that we are telling the driver and the validation layers, hey, we are going to use these features. Let's see if this works. Okay, this was the quickest upgrade to 1.3 probably ever. Now, the other thing that I want to do is that when we are building the shaders, we are saying we want to build the shaders targeting 1.2, and instead I want to target 1.3, just in case. I don't know what this actually changes, but you know, just in case it changes anything. Okay. Local size ID execution mode. No idea what this is. Do not care. What it wants us is to enable maintenance mode, which is fine because it's also part of the core. We could look up like what this was about, but okay, stuff needs to change. So when you look at the compute shaders that we use, we declare the layout of the compute, of like the threads that are running in the compute shader. So I'm guessing what happened is that in whatever SPRV version we just courageously bumped to, you have to use, so we actually need to look at the maintenance for now. You actually need to use a different, so like the shader compiler uses a different SPRV instruction to expose this data. And in turn, our SPRV parser that we wrote a while back, it's going to be impossible to find this out. Let's do this. So in turn, the SPRV parser, yeah, probably needs to recognize this thing. Because I'm guessing that, oh, I see, because previously you could only specify the size of your work group using constants, and now you can also use specialization constants. Do I want to embark on the journey? Do I want to embark on this journey? Let's try. Okay, this is getting more intense. Let's see what this thing is. Oh, this is a little annoyingly painful. So previously, to parse the size of the work group from the SPRV bytecode, you could just parse the instruction we just had embedded in it, like the numbers that we care about. But now there's an instruction that references the integers. And so to parse that, you need to parse the integers. We do some of this, so maybe it's easy enough. It's definitely a little annoying, but okay. Okay, so what we need, oh, maybe they have to be declared already at this point. Oh boy, this is more, we don't, to be clear, we don't have, like, the reason why we got here is because we upgraded the shader building process to use newer version of the toolchain, as a newer version of the target SDK. Technically, we don't have to do this, but let's see how painful this is. Because maybe it's all right. Oh boy. All right, so we are looking for local size ID. What? Why is it part of? Oh yes, all good. Okay, so what? Oh, okay. Yeah, so when we parse this, we don't know what the actual value is. Okay, so essentially what we need to do is that if this is this new thing, then I'm gonna assume it's the same, but essentially we first read the instruction that this is my first time actually writing code with Copilot, so the autocomplete might be a little wild. So essentially we need to parse this instruction. We need to remember the variables. Then when we parse the rest of this PRV code, we previously were just parsing the variables. Now we also need to parse the constants. Does it mean we need to parse the type? I guess we already parsed the types for some stuff. We have this parser for SPRV. Is it like op constant? Is that why? Okay. Okay, is this thing always integer? It's always integer. But I need to know. By the way, normally you would use like a library to do this, but we don't have a library. Instead, what we have is a makeshift PRV parser. And a copilot that this is actually accurate. This is a little, yeah. Copilot tends to be very surreal often. Like it often tells you a suggestion that actually sort of makes sense in the context. But it is absolutely right. It is the value, not the idea of the constant. But actually what I wanted to say is we currently only correctly handle 32-bit integer constants. So I don't want to deal too much with the whole like this constant can be of any type. I don't want to deal with this too much. So okay, after we have parsed stuff, we need some valid. Do we know the type of the shader? We know the stage. Yeah, okay. All right. It's kind of funny, like, so the Copilot has all of these beautiful suggestions, but the actual IntelliSense is like really terrible. The suggestions just do not work well. And like the typing flow is interrupted and stuff. It's pretty bad. What? The formatting is terrible. Oh my god. So Copilot is great, but everything else is pretty bad. All right, so clearly this didn't work. Actually, wait, this is strange. Hold on. Wait, how are we parsing compute shader without... Yeah? What? That was weird. What? Did something... This is interesting. Whoa. No, hold on, this makes sense. Is it the case that the execution mode... Oh, the execution mode ID. Oh. Okay, sure. All right. Okay, we are close. We have parsed something, but I think we're not parsing the value of the constant correctly or something like this. Oh, this is gonna be bad. Hold on. So really we need to go here. Okay, so we have the variable name. It's a constant thingy and it's 64. Oh, great. Why is this not initialized to something reasonable? Don't we zero initialize anything, everything? All right. All right. This is not how I thought I would spend the last 10 minutes, but the short story is encoding of the workgroup sizes in SPIR-V changed, and so now we support both the old style and the new style, but the new style is way more indirect. And so because of this, we had to parse like the constant data, and we kind of ignored the type, but whatever, it should be fine. I do want to know, so we have this typo, like, so the assert would have fired presumably, but what happened when... For some reason it said group count X. Oh. Right, because these were 0 and something, I guess, malfunctioned. Okay. All right, you know, whatever. Okay, so I think we're done with this. And by this, I mean... Okay. We've upgraded to Spear V 1.6 or whatever, like whatever goes with Vulkan 1.3. We are using Vulkan 1.3 device. We are requesting Vulkan 1.3 features. We aren't actually using any Vulkan 1.3 features yet. But now is the time where we can try to switch to dynamic rendering and see how that works out for us. All right. So, so as you can see, the 1.3 upgrade itself is very straightforward. The reason why we ran into trouble... Oh dear God, no. Hold on. I need to hand edit the project file. Why does it not complete? So the command line for compiling the shaders changed. Did I just not edit it in the right place? Can I just do this from the UI? Yeah, I didn't do the right thing. Hold on. Yeah, okay. I should have done it here instead of wherever I did it. Can I rebuild? All right, and let's double check that it actually uses the new path. Yeah, the change we made for this PRV parser should work in for the older blobs as well. It's just not okay. All right, so this is good and this is good. Okay. Don't actually know what version of SpearV this is. Let's find out. 1.5, 6, 6, 7, 6. It's probably 1.6. Let's see. Yeah, 1.6. Okay, cool. We have to change this. Okay, so now what you've actually all been waiting for is 1.3 stuff. So there's two features that I wanted to try that come with 1.3. One is dynamic rendering, one is synchronization 2. Dynamic rendering hopefully should be straightforward. Synchronization 2 is a little scary because anything that has to do with synchronization is a little scary. But let's look at dynamic rendering first. So I should mention Niagara is not like the perfect project to introduce dynamic rendering on, as in the gains, the value of dynamic rendering isn't that obvious probably on Niagara because the setup that Niagara uses for render passes and stuff is pretty simple. And so there's an argument to be made that like, why bother, right? Like Vulkan before dynamic rendering worked fine. But I mean, as long as it's not more complex, it's still probably a good idea. So let's try to figure out what that means. So we have all of this code that creates the render pass. And it is very specific. We assume a lot of very specific things because we only have 2 render passes. And we also have code that creates the frame buffer. The frame buffer is interesting, for example, because we actually have to recreate it whenever the swap chain changes. So like whenever you resize the window, some code needs to execute again. And we wrote all this code way back when. This was like the, you got to deal with this as long as you work with Vulkan. And the reason why we only have 2 render passes is that some stuff that we do with compute shaders. And this avoids the necessity of sort of having too many render passes. In fact, I want to say that we do this thing that you generally probably maybe shouldn't do. Yeah, which is that when we actually render to the frame buffer, to the to the window, let's put it this way, we don't actually render anything to the window, strictly speaking. We do all of the rendering off screen into a render target that it has the same size, and then we just copy data from that to the final presentation target for the window. And part of the reason why we do this is because I really didn't want to deal with like recreating the render passes whenever things change. Or you still have to do some of this, I guess. But anyway, like it was just render passes were always a pain to deal with, so we minimized their usage. As a result, when converting to dynamic rendering, there's only 2 render passes to deal with, so like it's not that big of a deal. But anyway, so dynamic rendering changes 2 things, and we might need to consult the spec a little bit because I don't know all of the stuff by heart, and this is my first time trying to use it. But it changes 2 things. One is that when you create the graphics pipelines, you no longer have to pass the render pass. And 2 is when you actually begin and end rendering, you don't have to pass the render pass, right? And you also, the frame buffer object doesn't like exist anywhere there. So these are the 2 big things. Now, before we go there, let's make a small change that we will probably remove later. I wanna hold on. So let's actually, okay, so this is going to be removed with the dynamic rendering code. This is going to be removed with the dynamic rendering code. This is going to be removed with the dynamic rendering code. Now, when we create a graphics pipeline, we pass in the render pass object. So instead of passing this, we'll have to pass something else. The thing I wanted to do before we actually convert everything is to measure the CPU overhead of beginning and ending the render pass. So we only have one place where we do this. It should be very straightforward. I forget what timers we use. Does GLFW? So I guess GLFW has a time function, which hopefully is pretty precise. And then do we aggregate something somewhere? Hold on. Okay, so double. The reason why I want to do this is, as I was mentioning, in theory, dynamic rendering is slower on the CPU, and I wanted to understand how much, like how costly is it to record the begin or end render pass command, really. And to measure this, instead of using a profiler like civilized people, we are going to use manual measurement like uncivilized people. How did I call this? Let's begin average. 0.925 for the old one, okay. This is fun because, yeah, the Copilot is pretty good. The suggestions seem to be pretty on point. Please excuse the slightly random naming of the variables. Okay. Now, to be clear, this is a tiny portion of the frame, or I am expecting it to be a tiny portion of the frame. But I still want to know, like, how much. And we'll probably have to measure it in... Let's start with measuring this in milliseconds, but it's probably going to be a rather small number. Okay. Okay. So we are running in debug, which we will switch to a different mode. Okay. We are measuring some numbers, which is good. I want to switch to microseconds because we are clearly talking about a rather small number. And I want to switch to release mode because validation layers have a large impact on the CPU performance of any Vulkan application. And because of this, we should not be measuring any CPU performance with validation layers enabled, which we won't. All right, so it looks like end timing is like nothing. The begin timing hovers between, you probably can't tell because it fluctuates so much, but it's basically around 8 microseconds. Let's call it just 8 microseconds. And we will remember this because as we change the code to dynamic rendering, now we will know like what the new overhead is. I don't know why this still is running. So, so the first thing that we need to do is to stop creating the render passes. But I actually don't want to do this yet, because I want to first stop using the render passes in creating the graphics pipeline. And I suspect this will break validation, maybe, because I think we learned last time that validation wants, or Vulkan specification really wants you to either use render passes or use dynamic rendering within a single pass, but not like mix the two. But maybe this is not actually true. I don't know. We'll see. And so last time we talked about the fact that yes, you don't have to specify the render pass when creating the pipeline, but what you do have to do is you have to pass the format of the targets that you are going to be rendering to. And it must be using some pnext nonsense. So let's see. I don't want to read the spec yet because a lot of this is reasonably straightforward and like, so there's this new thing called pipeline rendering create info. Heck, okay. Pipeline rendering create info, rendering info. So I don't think this is right? Yeah. So like sometimes Copilot just manufactures these things that don't actually exist, and it's not quite correct. So yeah, it's a little bit of a mixed bag. Anyway, I'm assuming the way this works is you need to attach this thing, and then you need to actually fill this with width. So this is for multi-view. We aren't using this, so I'm hoping we don't have to like care about this. And then you have to actually pass it the color attachment formats and the depth attachment formats and the stencil attachment formats. So I think what I'm gonna do is that I am going to just, instead of requiring a render pass, require the rendering info thing. And then I'm gonna fill it externally to this code. And just, instead of the render pass, like use that. Which means that here, when we create the pipeline, we need to say what are our formats going to be. And as we discussed, it's an unfortunate limitation, but it's kind of ingrained, like it's kind of part of the problem maybe we do this before we create the shaders. Yeah, let's do this here. It's kind of part of the problem that Vulkan is trying to solve, that there's so many architectures that it needs to support. And some of these architectures require the knowledge of the format that you're going to render to when rendering to. I'm now curious about some things around format compatibility, but let's not. Okay. Are we actually using the swap chain format for? Okay. So I'm assuming we don't actually use stencils. I'm assuming that you need to pass undefined, but it happens to be 0, so we might as well just not fill it. So this might be all you need to do to create the graphics program now. So you just need to pass the format. And remember, for our flow, like Niagara code was structured to make it reasonably easy to work with given the realities of the API that existed back then. So here the change seems super simple. Hey, okay, we created 2 render passes. Instead of this, we're just going to create this rendering info thing. Instead of using those, we're going to use this. But things are complicated in actual real world. And so the change that was simple for us to make here, we actually don't know if it works yet, but if it does work, it was simple to make here, but it would be complicated to make in a real application. Plus, even here, we have actually 2 render passes, but we are only using one of them to create the render, the graphics pipeline. And it is correct for complex reasons that I will not go into, but like, it's not always going to be this way, and it's really easy to get to something more complex. Rendering info in a real application. Okay. Actually, hold on. Okay. Let's probably look like this, I'm guessing. All right. And now I think we just leave this guy as null, and let's just see what happens. Cool. Okay, so we have successfully created the actual object for the pipeline state. But now what the validation layers tell us is that, hey, you are actually using the render pass objects to begin the render pass. And then inside them, you're drawing with the pipeline state object that did not use a render pass. And that's not okay. Not to worry. To fix that problem, we're going to have to actually use the dynamic rendering when we begin the rendering. So this render pass thing is like the render pass object that we have created. We are actually using here. Oh, this is neat. The reason why we have 2 is that so remember I was talking about the fact that we rendered objects twice. We render them, then we do some downsampling, pyramids, etc., and then we render again the objects that haven't been rendered in the first pass but need to be. You can technically skip this second pass, and things will technically work in our example, I think, because we have only we have a static camera, and so the visibility of objects is like constant actually, right? But once you start moving the camera, the second pass becomes important. So the reason why we have two is that when you start the second render pass, when you start the first one, you want to clear the color buffer and depth buffer. When you start the second one, you don't want to do this. And this knowledge is embedded inside the render pass, which means we have to have two. But actually, this is not the driver can't pre-compute anything interesting based on that information alone. So actually, this is not even a useful the fact that we had to duplicate the render pass doesn't convey any fundamental truth about the graphics API behavior or graphics driver behavior. It's just that way because Vulkan was specified this way, which is part of what the dynamic rendering feature is meant to solve. So let's just say that instead of passing the render pass, we already passed the slate boolean in a few other cases, so we'll just pass that instead of the render pass. I don't like unadorned booleans, but I like this style. So we are calling it twice now, and now inside this function we can't use the render pass object here, and we can't use these commands. We have to use different commands. So for ending, it's I think end rendering. So this is a little nuts. So Copilot is awesome when it works. Is Copilot interfering with autocomplete? And rendering, I want to say, yeah, okay. So like it knows that the function exists, but why can't it complete? All right, let's stop ranting about Visual Studio and write code. I already used the term rendering info. Okay. So let's see what we actually need to fill. There's going to be a little bit more code here than right now because a lot of the stuff that we pre-filled when creating the render pass, we now have to fill here. So let's see. There's some rendering flags thingy. So this is important when you use like if you want to split a single render pass into kind of two halves and do some of this work in other command buffers, etc. This is important. We can't actually do this because for us, we like render something and then we do a bunch of compute work and then we render something again. So we have to break this, so for us flags are not interesting. Render area we already fill here, so we are gonna just copy that here. Layer count, I don't know, I guess we aren't using layer, there's like a feature for this, but we aren't using it, so presumably this can be 1, presumably this can be 0. And then we have to actually tell, like, okay, when we created the render pass, we said this object aggregates all of the knowledge about where the render goes to. Now that the object is gone, we have to actually tell the driver that we are rendering to some specific color targets and things, all right? So we have a color output. We have one color attachment and and we have one depth attachment, and these are both using this thing. So now we have to fill that. So sometimes Copilot is just very terrible. This is what bothers me around about okay, wait, this was actually correct. So with tools that help you write code, there's this difficult kind of problem that you have to solve, which is the tool can't just be helpful, it also needs to be reliable. A tool that is helpful but unreliable in how helpful it is, how correct it is, how quickly does it respond, etc., actually stops being helpful. Even if it technically gives you good information, like if you can't rely on this information being there, then you can't like actually use it. So this whole API was built around render passes. Dear God. Okay, we'll need to rewrite some stuff. So so the Copilot makes some things like nicer, but the fact that it unreliably displays unreliable information is a little problematic. All right, so we aren't using MSA. Hopefully we can just drop all of that. So what we do need to fill is this image views, which should be straightforward. So we are rendering color to this actually might be correct. No, this is not correct, of course. We're rendering color, we're rendering both, in both passes we are filling two buffers, color and depth. Color is color target, depth is depth target. And we have this frame buffer that we will stop using, which means that we can render here. When we are rendering to color buffer, we use color attachment optimal something. Okay. Then here comes these load and store operations. And this is the thing where we had two render passes for. And I actually can just copy this out of like the render pass descriptions, because we are passing the same data more or less. It's actually a little less verbose. I think we will lose the total number of lines. Like we will use fewer lines in total, which is good. But also this information is a little bit more readily available. And it's a little bit easier to connect. Rendering no pass info. It's a little bit easier to connect to the flow of the code, because now when you're stepping through the code, you're like, oh, cool, I'm rendering to the color target. And then in the early pass, I use clear, and in the late pass, I use load. So all of this is a little nicer, in my opinion. And then this clear value, we need to actually copy out of. So we'll need to refactor this. This is let's leave it like this for now. And then depth, it's the same stuff. And then here is depth target. Here it's depth attachment optimal. I think these are the same. I want to say. And there's the similar problem with clear. I think that's kind of it. We don't need this pass begin and for. Now the problem is clear values. The problem there is a little stupid. It's just that we passed like two clear values. The way that the render pass was structured is there were two attachments, color and depth, and so we had an array of two, and we just passed an array of two. So probably what we are going to do is we are just going to pass these separately. And then we are just gonna not use, they are effectively gonna be ignored unless you actually clear. And so specifying them again isn't like a big deal. If we wanted to, we could pass in pointers and use null and stuff like that, but it doesn't matter. The big thing is all of the refactoring decisions with dynamic rendering are very local to the code. We have the function that is called from a given place. It needs different arguments. Let's pass it. Previously, the knowledge about the render structure was split between two places, initialization and like actual rendering. And this actually made it more difficult to refactor code. Now, if some of this code doesn't isn't very good, I don't even care. How the heck does this work? Wait. Oof. How does it initialize? This is actually... Interesting. All right. I don't think this is super correct because like you need to initialize the correct member of the union. I don't think it initializes the right one. Oh, actually, this is good because now we can make the code more type safe to fix this problem. So we had a hidden bug in the code. The reason why the bug didn't manifest is that the clear value was for depth was 0, and so the whole struct was initialized with zeros and like it didn't matter. And the reason why we had this bug is because the stupid render pass API forces you to like not differentiate the types of the values, and so of course we missed it. All right. If it wasn't obvious yet, I really like the fact that dynamic rendering happened. So happy about that. I don't like the IntelliSense behavior. It's just a little broken now. Color depth stencil. Okay. All right. So like I press Control Space and it takes like 3 seconds to complete. Like, what is this? I should disable. I enabled Copilot because I don't actually use Visual Studio much to write code. I write most of my code in Sublime these days. And I use Visual Studio to debug and profile occasionally. And so I figured, hey, like I'm just gonna keep it there, and in case I want to play with it, you know, it's like an environment where I don't mind that it's on because I don't use it much. But now that it's on and I'm typing code, I actually do mind. Look at that, the code works without issues. Like we have the 0 validation errors. I mean, hopefully there's no bugs. Okay, let's kill all of the functions that we don't need anymore to prove to ourselves that we are free from the tyranny of the render passes. Oh, we are still not free from the tyranny of the render passes because we destroy them and then we destroy them here. Oh god, and the frame buffers were terrible. How can it... Did we like not create? I see. So here we do need to say that we need to create something first time. All right, let's check that resize works. It does. All right. Now, let's double check performance, right? I want to remove the performance markers that we added because they like, it doesn't matter that we spend a couple microseconds, but just in case. So I think we said 7 to 8 microseconds for beginning recording and basically 0 for ending. And look at that, it's the same number. So the cost of beginning dynamic rendering is exactly the same on AMD drivers for our specific use case between a pre-created render pass object that ostensibly has all of the data that it needs to like cache in the driver or whatever, and just doing this all from like, you know, just fill the structure, pass to the driver doesn't know what it needs to do, it just does everything from scratch. So this is great. So from this perspective, like there is no downside to using dynamic rendering, right? You are not gonna lose, except for the fact that dynamic rendering is a Vulkan 1.3 feature, which is not widely available on the previous versions of the API, right? So caveat aside, otherwise it's great. So let's delete the timing, because, you know, like we don't actually need it. And we got we got like the validation layers were very correct and very helpful, right? Because they told us that you can't mismatch, like you have to either use dynamic rendering or not within a given pass. Just out of curiosity, so we didn't use a lot of render pass specific code, right? But we added 42 lines and removed 98, so we removed like 50 lines of more than 50 lines of code by switching to dynamic rendering. Again, you know, if you actually need to support older APIs, there's older versions of the API, you can't just do that, but hey, it actually simplifies our code, it didn't make performance worse, it made it easier to refactor. We caught one latent bug with clear values, which we couldn't easily catch before, and the reason why we couldn't catch it easily before is because you had to shove the clear value for attachments of different type into a single array, and so you had to like break the type safety essentially of that array because it has two distinct types in two different slots, and we didn't notice this, and so the code was broken. So like, I don't know, it feels like a win-win-win-win-win from just like every possible perspective. And it was super simple. Like we spent, what was it, I don't know, half an hour on this. Like it was easy. So dynamic rendering, I call it a success. It was super simple to convert. We hit 0 problems during this. Of course, our structure is simple, but you know, and this unlocks options. Like we could now say, oh, now it's actually not very painful to have to target the actual window swap chain target with a render pass instead of like copying to it using a command, right? So which could mean that, you know, we can save bandwidth. We are wasting bandwidth on this copy, so like we could stop wasting bandwidth on this copy now that we use dynamic rendering. So and the reason why we didn't do this is, again, render passes were just too painful to work with, so we didn't do that. Now we can. So huge success in my opinion. Things work really well. Validation layers are helpful, like all of this, like thumbs up. Drivers work completely fine with this. Keep in mind the Vulkan 1.3 release happened, what is it, like 4 months ago or so? So obviously, you know, I'm not the early adopter here, but hey. So let's double check. So we deleted a bunch of code. We need this, we need this. No frame buffers anymore, no render passes anymore. Have to fill this thing. And like, it's important probably to recognize that, so this code that we have written, you basically need every line of this code. I mean, except for like the fact that you have 3 structs, which is completely fine, but like it's sort of noise in the sense that it doesn't convey like useful information. But you need everything. We are telling it where to render. We are telling it about the image layout, which is important for complex synchronization reasons. We are telling it what to do when you start, and if we stop telling this, we will actually, like, the driver will not know to clear. So it's important. We are telling this what to do when you store, clear values, same thing for depth. We are telling it the size. This may seem like redundant information, as in, doesn't the driver know the size? But you do need to tell the driver the size because you can actually render to a subsection of the targets. The targets may be different size, etc., etc. So like you do need it. I don't know that you need the layer count. You probably do. It's a little bit redundant. Maybe you don't actually. Let's see. Yeah. Layer count must not be. If view mask is 0. Okay. So you do need layer count for some complex reason, doesn't matter, and then you just pass it the arrays. So like this code is pretty information dense. You're actually telling the driver what it needs to do, and you're telling the driver what it needs to do when you need to do it, not like when you start the app. All right. So let's commit this. Day 16 dynamic rendering works. This is great. It works well. It works well. It's as fast as render passes. We don't know if there's a GPU cost, but like let me tell you, there's no GPU cost. Definitely not on this GPU, and in general, it's nicer with respect to code flow. It helped us find a latent bug with respect to depth clear value. It requires fewer lines of code. We no longer need to carry frame buffer and pass objects around. Just like everything is good about this. All right. So if we look at our list, we did do this, which required a little bit of spear reparsing. We did do this, although we gave up on GLM, whatever. We did do dynamic rendering, including timing, and concluded that there's no difference. So the only remaining thing is synchronization and sync validation. We are coming up on the 3rd hour, though. So that is, I'm trying to figure out if I wanna, how much of synchronization I wanna do. It would be good to just convert. The thing with synchronization 2 is, for our case, I don't think it makes anything nicer. Synchronization 2 has better split bearer support. However, one, our frame structure right now, I think is pretty serial. I think it's going to be difficult to use split bearers in a way that actually improves performance in any reasonable way. Which is not going to be the case for more complex applications, but I think it is the case for us. And then the other thing is to actually know that you're taking advantage of the split bearer feature, you need to profile something, and that will take us time to set up. But I don't even think let me look. I don't even think it's very interesting. As in, like, I don't think there's a lot of value in split bearers in our case. Yeah, and then there's call render. And then you do pyramid generation, which is dependent. Pyramid generation is not implemented very well right now, just in general. It serializes for every pyramid level. Like we use individual compute shader steps to do that. So this is like bad code. It's pretty fast in practice, but it's like not the efficient way to write this. However, it is split bearers wouldn't help improve it, and it does take 0.6 in full screen. Oh, a full screen is 4K, by the way. So I know you're watching this on a 1080p stream, but the full screen should be 4K. And my video encoder downsamples it. And so like at 4K we are taking I can't even see this, 0.4 or something milliseconds on the GPU. So it's pretty bad code. We can probably save 0.1 or 0.2 milliseconds on this in 4K. Does it matter? I'm not sure. But it's plausible that we can. But to do this again, you need to rewrite the whole thing. You can't just like use split barriers to make this thing faster. So, and then after this, we just do render, call render again. And then after this, you blit. So there's no use case for split barriers in this code. There's also no. One other nice thing about the synchronization tool, for example, is the fact that when you have to combine barriers from two distinct stages, like you have a barrier for compute and you have a barrier for rasterization, you combine them, it's more efficient with synchronization 2 usually because of the way it merges the masks. But I don't think we do this either, because render is raster, call is compute, pyramid is compute, a series of compute passes. And so there's no interesting barrier anywhere where I think things like that happen either. There is one thing, sorta, so like here we combine two barriers from two different raster stages. But let's try. The good thing about synchronization 2 is, so for render passes, we have to convert two parts of the program at the same time, the pipeline management and the render pass management. Synchronization 2 is much more piecemeal. You can say, I have one barrier that I want to convert to synchronization 2. Let me do that. So we can do that, and we can see what happens, but it won't actually result in anything meaningful in terms of like code size reduction or whatnot in our case. So it's a much more cosmetic update. So optimize styler API, two things. One is I can't comment on future work that is happening around this. Two is even dynamic rendering is styler friendly if your render passes are single subpass, right? So you shouldn't be afraid of using dynamic rendering on mobile again. KVAT, Vulkan version, is the feature supported? It's a problem. Once this problem is resolved, should not be afraid of using dynamic rendering on mobile, except that if you had complex, crazy, like 5 subpass render pass structures, then it's going to be painful because currently there's not a feature that you can replace that with. And if you happened to had efficiency gains from tilers in your complex setup, which is complex to establish, but if this works for you, then currently there's no replacement. All right, so let's try this. The one thing I wanted to make sure before we try synchronization 2 is, do we actually have synchronization validation enabled? The reason why this is important is this feature wasn't available when we were developing Niagara, and so we made a bunch of synchronization errors. Now, finally, thankfully, there is a way, like the... Why is this not used? Oh, it's like a full barrier, right? This is a nuclear barrier, all right. So now there is a way to enable validation that actually tells you when you forgot synchronization, but I don't know if we enable this. Let's just, just accidentally remove a barrier. Okay, clearly synchronization validation is not enabled, because I think we can just remove all of the barriers. Well, Well, image layout, right. So yeah, you can't remove all the barriers. Is it this one? Yeah. But you can remove most of them. All right. So the first order of business then is to actually enable synchronization validation, because without this, working on synchronization code is just like not something you should be doing now. It used to be that you didn't have this option, but now you do have this option. I don't remember how to enable it, so we'll need to figure that out. So I think there's like a layer. So I guess what we need to do is vk get layers. Oh, interesting. Okay. vk get instance. This is not the code that I wanted to see. vk enumerate. All right, I'll have to Google this. I don't remember how to even look at the layers. Looking inside the spec for this is probably not the best idea. Oh, right. Oh, no, yeah. Wait, all good. Yes, okay. So device layers don't exist anymore. How do I enumerate instance layers? Because I can request them. All right. Clearly, we need to actually look at this. Okay, so there's a layer called vk layer Cronus validation. Wait, no, this is the summary. Synchronization validation. I don't want to. I know I can enable this with like a tool, but I kind of want to enable this in the code. Oh my god, people. Where's the actual API for this? This is killing me. Is there like a flag? Aha, there's a flag. So if you use this thing, then there's a flag that you can enable. There's a bunch of other flags that you can enable. But this is the important one. And so, okay, so we need this extension. Wait, I didn't Google the right thing. It doesn't matter. We need this extension, yeah. All right, so this seems to be a recent extension. Okay, so pnext, when you create the instance, you need to pass this thing, and then inside this thing, you need to tell what you need to use. Okay. Okay, we are not using pnext yet, which is good. So I guess we will just hook up here. That's definitely not. This is not even valid. Right? Oh, it is valid. Oh, okay. Never mind. I take it back. Okay. Well, this is a very... Wow. I mean, I know why they did this, but an enum flag would have been better. Okay. This is so frustrating. The way IntelliSense just doesn't work. Can I just disable Copilot? It was maybe a bad idea. I'm not sure if it's Copilot, but it feels like it's probably Copilot. Let's see if this is actually true. And I don't know, maybe I should remove. Okay, it's clearly still enabled. Do I restart Visual Studio for this? Maybe IntelliSense is just broken. Like, I don't know how these features connect. No, it was Copilot, of course. So Copilot just breaks IntelliSense. Cool. Wow, okay, this is so much better. Except that I can't complete this thing for whatever reason. Yeah, but okay. But okay, IntelliSense still doesn't work very well, but it works better compared to when Copilot was enabled. Okay, yeah. Do we use size off? We do use size off. Yeah, now I can like press Control Space when I expect things to complete, and they complete quickly. Oof. All right, so we have enabled heroically synchronization validation, and it's gonna tell us that there's a hazard read after write for some buffer, blah blah blah. Okay. The downside of synchronization validation, let's see if it changed, but this is how it used to work. Yeah. So let's see if our code was actually correct now before we started removing the barriers. It looks like things got better. Last time I tried synchronization validation, it told you correct information, but it was difficult to pinpoint like where the problem is. It feels like now it's a little easier. Let's see. All right. The bad news is things don't still work. Okay, so for us to actually embark on synchronization 2, we probably should first fix synchronization 1 hazards. Oh boy. The problem with this is that I will need to like, it's all right. It's complicated. I don't have the mental fortitude to actually explain synchronization stuff. So let me just attempt to fix synchronization errors and then we'll see. So this is saying we are reading from the buffer, which we really should have named, but we haven't. But there's an extension for this, which, okay, whatever. So we are reading from the buffer, from a storage buffer. And the previous access was a write to that buffer. So this looks like, okay, so this is during our actual rendering. And before rendering, we were filling some buffer. Let's see. I think it's this, I guess. So we are reading the draw commands buffer. Oh, we have this funky setup, I think, where we ls like are we even reading from this? What are we reading from this for? What? You can tell it's been a while since I looked at this code. What is this interaction? Yeah, but shouldn't these guys be sequential? Why are we even using that? Maybe there is some reason in the mesh shader path? I'm confused. Oh, of course they're not sequential. Right. Okay, so let's see. Yeah, so when we are filling draw commands, right, so when we are filling draw commands, we are filling the structure, and the draw ID is the index of the mesh data with like transforms and stuff. And so we bind this buffer as a storage buffer inside the shader because we need to read the draw ID out of the structure. But we also cheat. And I believe this buffer has the layout that is the same almost as required for the draw indirect. And so when we do indirect draw something, when we do draw indirect, yeah. So we ls stuff in a weird way. Like instead of having like 3 buffers, which just was like painful and probably unnecessary, we have like one buffer that collects a bunch of info inside it, and then when we tell it draw indirect, we only when draw indirect happens, the GPU is reading from this part of the struct, but the shader also needs to access. Okay, so the validation layer is telling us that the shader is reading this draw ID from this buffer, and that it looks like we had a barrier for the draw indirect synchronization, but I guess we didn't have a barrier for the usage of this as the storage buffer. So to figure that out, we need to go to the code that is writing this, which is the calling code. And look at what happens there. So the calling code, oh yes, indeed. So the calling code, there's like 2 buffers, one is a counter buffer, doesn't matter. But so the calling code says, after I'm done writing to this buffer is going to be read by the indirect command stage, which is true. But what is also true is that it's also going to be read by by shader stage as a storage buffer, and it's going to be read in the vertex stage. Stage vertex shader, or when we use mesh shaders, it's going to be read someplace else, I guess. This is the part where we can't actually test this code properly, but whatever. So we are reading this, oh, hello. We are reading this in the mesh shader, and also in the task shader, and also in the task shader. All right, so basically whatever vertex processing happens needs this data. I don't know if I can just like, are there even enums? There is enums for the NVIDIA stuff. I don't know that I can just like use them here if mesh shaders are enabled. So let's just call it rasterization stage this. But actually, if mesh shading is enabled, which I don't remember how you check, I guess like this. So I believe the correct way to do this would be this. Okay. So this fixed one error. We have the next error that we need to fix. Let's look at this. I think somebody ran and fixed some of this stuff before, but validation errors improve. I was talking about this at some point on some Vulkan streams, but validation is this. I'm very convinced that there's not a single program that gets validation right in Vulkan out there in the wild. And it's just a question of, is there a validation yet that tells you that you have a problem or no? Like, is the problem visible or no? All right, so what's going on here? Oh, it's on the pipeline barrier. Hell, hold on. Right after write for image barrier. Layout. So it says that we were writing to this as the storage write. In the dispatch. So this is probably the pyramid. Yeah, so like there's a depth pyramid, and the depth pyramid was being written to from the compute stage. And we need to transition it. Is this the first frame? Is that the problem? Because like, no, but why does it care? Hold on. No. Prior usage, storage write. One other problem with barriers is that when you have multiple frames, like sometimes you implicitly, from the barrier state perspective, sometimes you implicitly depend on the previous frame, and like it's very easy to get that wrong. So like I'm trying to, I don't even know if it's the first frame. It might be that it's not. Let me look at the code. Oh, it's the late render. I see. Okay. So we rendered the pyramid. Okay, so we rendered the pyramid. Then we use the pyramid in the compute shader. And then what are we doing with this? clear. No, no, this is calling. Sorry, the Visual Studio confused me. So we are in this function, not in this function, because the breakpoint. Okay, all right. So during late calling process, we have filled the pyramid data from the compute shader, I guess, because I think this is where, yeah. And now we are transitioning the pyramid. Why are we transitioning from undefined to general? That makes no sense. Why is it from 0? Who wrote this code? I know who wrote this code. What? This is wrong. I think I wrote this code, but this is very wrong. What the heck? Shouldn't even be doing this. The early pass doesn't do calling. So this is all weird. I don't, why is it 0? Why does it go from undefined to general? This makes no sense at all. So let's look at the pyramid code. So there is this image. We rendered the depth, and now we are filling the depth pyramid by reading from the depth and then writing to the MIPS. And then the actual pyramid image is represented by these MIPS. And these MIPS are just always in the general layout because we only ever write to this thing or read from this thing, presumably, from the compute shaders. This thing says texture LD, so here we are actually using sampling. Oh, and we do need to be using, okay, this is all coming back to me. So we render to the, right, but we keep it in the general layout, right. So we render to the depth pyramid, then, and downsample it, so like we build it. All of this happens in the compute shader. Then we start reading it from the shader, but when we read it, we keep it in the general layout. Why is the transition from undefined to general? This makes no sense. Why is it from 0? Because we were just writing to it from the compute shader. What? Okay, so I think what is supposed to happen is that we were writing. Now there's some trickiness around this because the pyramid was in the first phase of calling, it is not used. So I think maybe there is some trickiness about this. In the first phase, we shouldn't even be transitioning it perhaps because we don't even use it. But this is where there is this problem where on AMD we had to apply this workaround. And so now we, like, the shader sort of uses it, but actually never does. This is all connected in very weird ways. I don't know. It's going to be interesting. Let's just say this, that in the first pass, we are going to keep the, wait, where did the 0 go? Is that the 1? Okay, the 1 is a 0. Oh, what? Never mind. So in the first pass, we actually don't read the pyramid data. We might still need the barrier because the shader has the pyramid bound to it. And the usage is guarded by a branch that, because of the MD workaround, depends on some static data. So like, this is probably why the beta was there in the first place. Now, in the second pass, we actually are legitimately reading the pyramid data that was just written. And so what we need to do, I think, is we need to say, well, actually, a shader was writing this data, and it was being done in the general layout. And, you know, yay. Okay. If you couldn't follow this, I don't blame you. Synchronization is tricky in Vulkan. We fixed a couple bugs. Don't treat this as a statement that our code is now correct. By the way, let's check if... All right. Oh, by the way, you saw it flickers for one frame. This is because for the first frame, the two passes, the one of them is like redundant because the visibility data is not even there. And so, yeah, like it starts, the bug on the MD hardware that we had to work around only affects subsequent frames. It doesn't affect the first frame. Anyway, so yeah, so okay, so the validation layers were correct. There was a bug here. This is impossible to understand for somebody who hasn't like this code is way too obscure. So first, this is a pyramid bearer. Second, let me actually group these, and then I'm gonna write a comment. So for late, we are guarding against writes, and then the layout. All right, so this is not easier to read, but I will write a comment that will help. And I think I can't drop any of these conditions, because if I do this, something else will fail. I'm sorry I'm not explaining this, it's just, it requires so much exposition to explain why some of these things are correct. But I'm gonna write a comment, and maybe the comment will help. All right. Doesn't read pyramid data, but all right, so I don't know if you can follow this comment. In Vulkan, there is this really annoying problem, which is that often you expect that the resources are in a somewhat consistent state throughout like the frame. For example, the depth pyramid here, we actually always keep it in the general state. However, when you create it, it doesn't start in general, it starts in undefined, and you cannot change that. you can change it for like some initial, whatever. This means that on the first frame, a layout transition from general to general is wrong, because on the first frame the state is undefined. After the first frame it's all fine. And so the reason why we need this stupid barrier on like the first, for the pass that doesn't even use the pyramid, is because of this first frame issue. I'm curious actually if maybe, so if we actually used specialization constants, then it's possible that we would have been able to avoid the barrier. We can check if this is true. Obviously the code wouldn't work, so like we can't actually do this, but we can check. Let's check. I think this is how you check. No. Yeah, okay, so it's like we buy, there's too much extra stuff that needs to change. All right, whatever. At this point, if we actually had two separate shaders, things would be maybe easier for us, but then we would never have discovered the validation or the specialization constant bug. So, all right. Notice we haven't even started doing synchronization 2, but at least our code works now, which we can claim with more certainty than we used to be able to. All right. Synchronization validation. I will note that Vulkan synchronization is really difficult, but the validation layer did a really good job. So to me, who understands the synchronization model pretty well at this point, it was easy to look at the message, say, okay, I must be missing this specific thing. Let me look into that specific place and let me fix it, which is really good. If you don't understand synchronization in Vulkan, then it's going to be very difficult to use the validation, of course, because like it's going to tell you, like it doesn't tell you how to fix the problem in a sense. It tells you where the problem exists. And so you need to understand how the model works to actually be able to fix the problem. All right. So, yeah, so the barrier is for reading the pyramid in compute shader. We have written the pyramid in the compute shader, and now we are going to read the pyramid in a different compute shader. So we have written the pyramid in the pyramid compute shader, which downsamples the buffer. And then we are going to read it in the calling compute shader, which is actually going to read it. And so, yeah, this write is for the write from the compute stage in the pyramid pass. And this read is for the compute read in the call pass. Assuming you were asking about the pyramid barrier specifically. The fill barrier name is also terrible. Oh, this is actually a counter thing. All right, whatever. Oh, it's called field because okay, whatever, it's fine. All right, let's not mess with this code too much. So I don't want to convert the whole thing to synchronization 2 because it's already been 2.5 hours. Let's convert one barrier to synchronization 2 and then call it a day. Let's actually convert this thing. It's freaking scary, but like it would probably help. It would probably help understand me. And maybe everybody else, like the differences between the synchronization 2. So we already talked about this barrier pyramid a little bit. This call combines two barriers. So one is that. The other one is funky. Oh yeah, this is actually a really good. This is a good barrier to convert. If I had picked one barrier to convert, it probably would be this one. So the other thing that this does is this. So the calling stage appends a lot of draw commands to the not command buffer, like an array of command structures. To be able to do this append, it needs to know which index to append to. To do that, we use a pretty classical idiom where we have an atomic add in the shader, and the thing that we are adding to is in a buffer, in a very small buffer that just has that. However, we need to initialize this buffer, this value with 0, because you need to start at 0 and then you increment it one by one and then write, right? To write 0 to that, we use this fill buffer command, which conveniently allows us to just zero out the buffer as long as it's like reasonably small or something. But of course, in Vulkan, you can't simply fill a buffer with 0. You have to say, oh, actually, I'm going to fill you with 0, but you have to wait for this fill to finish before the operation with that buffer starts in the compute shade that follows, right? And so because of this, there's two barriers here that we combine. One barrier synchronizes with the fill with 0 that we have just done. The other one synchronizes with the pyramid fill that we have done previously. There is some opportunity to make this thing a little faster, but we need the profiler for this, etc. So like, let's just roll with this. It's not a huge deal. So this means that we actually are synchronizing between compute shader and two different stages. One is transfer, where we write data. Right. One is transfer, where we write data, and the other one is compute, where we write this other data, right? But because of how synchronization 1 works, some of this data is specified like once for all of the barriers that you are submitting, and some of this data is specified per barrier. So without further ado, let's see what is required to use pipeline barrier 2 here instead of pipeline barrier 1. So instead of passing like a whole lot of data, you instead just say, I have a bunch of, oh no, I have the dependency info. Oof, okay. I have the struct that I want to fill. Now that we don't have Copilot, it doesn't fill these guys. But it's fine, we can fill it ourselves. So this is annoying. I would probably wrap this a little bit, because you have to like create a new local variable every time you need a barrier and stuff. So we will keep the flags. I don't want to go too much into this. And then you have to specify roughly the same data. Actually, like if you look at this function, it had dependency flags, memory barrier count, memory barriers, buffer memory barrier count, etc. So like it had these 3 arrays of data, and it's the exact same data that you provide here. If you just do it in a struct, which is important just in case you need to extend the struct. But for us, essentially, we have one buffer barrier, and and it's this fill barrier that synchronizes with the 0 with clearing of the buffer that we have just done. And we have the second one, which is the image memory barrier, which is this pyramid barrier, right? And these types are new. So here we use image memory barrier. Here we are going to use image memory barrier 2. Oh. So this is going to be pyramid. This is going to be fill barrier. Now I'm using these helpers that fill like it's basically just a helper for filling the structure. And I guess we need a version of this for synchronization 2. But we'll need to change so the layout is the same. This is the same. Really, the only difference is one, instead of access flags, use access flags 2, which isn't a very complicated change. Oh, do you still need the aspect business? Don't think you need the aspect business. So I think, is that true? Interesting. Oh, it's part of sub-resource range. Never mind, you still need the aspect. Okay. So one change is you just switch to a different version of the enum. Which is different because it's 64-bit. I talked about this, I think. And then the only other change is that instead of specifying the stage where the access happens separately, so like I am reading this data in a shader and the read happens in the compute stage. Previously, this was split between the barrier structure and this other parameter to the function. Now it's all in one place. So you need, bottom line is you need to specify this guy. Oops. Pipeline stage flags 2, SMC stage mask. Destination 2, not 3, and then okay, I think this is about right. Oops. All right. And then this is going to be very similar, but like a little different. So you need 2, there's probably an underscore here. You need to fill stage masks. I'm just going to blindly assume that if the code compiles, it works. Like maybe there's some extra stuff that I forgot just now when upgrading this, but let's just assume. All right, there's like some changes around all of this when you use cross queue barriers, but we don't care because we don't use them. All right, so we are gonna be using these shiny new functions with 2 in the name, and I'm gonna split this a little bit. Oh, actually for the image one, now it makes more sense to reorder the parameters a little bit, because I'm gonna put the layout here so that it's all a little bit more neatly organized. Okay, so this is gonna read a little bit better, hopefully. So this is what we need to, it's the same information that we were communicating previously, but we communicate it in a slightly different style. We are saying that for this pyramid, we have this weirdness with 2 passes, but in the second pass, we have a compute shader, pipeline stage compute shader bit. And otherwise it is 0. Can you do, probably? Okay, let's see if this works. So to transition this pyramid in the second stage, the access before the barrier is that the compute shader writes to it and the layout is general. And then there's this weird business with the early pass that we will not talk about. And then the access after the barrier is going to be again from the compute stage. But we are going to read from the shader and it's going to be the general layout. So the first three are what happens before, the second three are what happens after, right? And then for the buffer, for the buffer, there's only two things you need to specify because you don't need to specify the layout. But before the barrier, what actually happens is that the transfer stage writes to the buffer. This is because this fill buffer command is part of the transfer stage. And then after the barrier, compute shader both reads and writes from the resource because we use an atomic increment, which is a read-write operation. And I usually like to group things like this so that there is like a before and after on separate lines. Here, if I were to attempt this, oh no, it's not too bad actually. Okay, cool. So this is it. Now I'm using, there is also like, because the enum got versioned, I think you can do this. But I think it's the same constant. Let's see. If it's not, then this is going to be a nightmare from the types. Oh god. Oh, this is transfer. Hold on. Not everything is lost. Okay. I think the constants are compatible. If this wasn't the case, this would be a nightmare because C doesn't allow you to use type safe enum flags in like a reasonable manner. And so it would be very easy to get things wrong. Okay, so I think this is right. Let's test this. Now I'm assuming that the synchronization validation code correctly validates synchronization 2. Let's check this. The bug that we had before with this barrier was that for the pyramid, we were essentially not saying that the pyramid was written to from a compute shader. So instead of this access before, we said, oh, actually nobody writes to the pyramid. You don't have to worry about this. And it's just going to be undefined. This was the pyramid before the fix. The pyramid barrier before the fix, I think. All right. And we got an error, hazard, right of to read, blah, blah, blah. Okay. So the one other thing I want to do is specifying this every time is going to be annoying. So instead what we are going to do is we are going to have one more helper function, which we'll call pipeline bearer, which will take command buffer. And it will optimistically assume that you only need image and buffer barriers. The memory barriers are very heavy-handed. It's like synchronize everything between these two stages, and they're usually not, they're sometimes not as optimal on real GPUs. So, like if you can avoid using them, and we'll call it pipeline barrier 2, I guess. If you can avoid using them, that's good. But we will need to specify the flags, dependency flags. Dependency flags. And then in Vulkan API, I think buffers go first, right? Oh, in this API it doesn't matter. In the old API, buffers went first. Yeah, okay. I guess we can do size t, although it's not like you can actually have that many. Image memory barrier to image bearers. All right. And inside this, we are basically just gonna put this boilerplate code. And this boilerplate code. Buffer barriers. Buffer barrier count. The reason why we need dependency flags is that rasterization barriers usually want you to specify this flag. Sometimes want you to specify this flag. I don't think we actually care. In fact, I think we might be using this incorrectly in some places. But this essentially says, if you write to a texture and then read from the texture, I think this says something to the fact that the read access to the texture is local, as in if you split the texture in half, and if you read from the left half of the texture, you can only wait for the writes that happen to the left half, if I remember correctly. And so this is something you sometimes want to specify on rasterization barriers. Anyway, this allows us to basically say 0 flags, 1 fill bearer, 1 pyramid bearer, and call it a day. All right, and now we have converted successfully one barrier to the new style of the API. Now that we've done this, it's probably easy for us to convert a bunch of other stuff. For example, here, it's almost mechanical. It's like you use the new structures, you specify the stage and the mask together. So I'm literally like copying and pasting things from one place in the code into another place in the code. And then 0, 1, pre-fill barrier, 0 null PTR. Right, and then we can convert. So sometimes it may get a little bit more repetitive, because like sometimes the fact that you have to specify where the access happens for every resource means that if you had a bunch of resources with the same access pattern, then you have to specify it a bunch more times. But often it's not actually, often it's actually different data. So here, this is actually an interesting case. This is going to be the final thing that we're going to do. We are almost 3 hours in, so we will call it a day here. But let's look at this thing. This is also better that we just fixed today. So there's two buffers. One is commands, one is counter. Commands are being used, both of them are being used by the drawing direct command itself, which is why both of these say, oh, I'm like the drawing direct command is gonna, the type of access to this resource is indirect command read. However, the counter buffer is not read by the shader, by the rasterization shader, by the vertex shader and whatever. And the command buffer is because we were reading this draw ID out of this. So this resource has shader read. This resource doesn't. However, when we specify the barrier, we say, oh, we are synchronizing compute shader stage, which is where both of these get written, with both drawing direct stage, which is where the command of drawing direct gets processed, and the rasterization stage, which is where the resources get accessed. technically the counter buffer has nothing to do with rasterization stage. It gets accessed by a different stage. So there is this conflation, and the new API removes this conflation. So it's often going to be the case in this code, at least, where we actually, it's not just blindly copy and paste. It's like, oh, actually we were specifying something that is too broad of an access, and we can like reduce the scope. So here we are, all of the writes here happen from the compute. I think we will need to move this guy here, yeah. So we are using barrier 2, all of the commands, all of the writes happen from the compute, and then the command buffer has this weird dual use, which I don't know if I would actually fully recommend this in practice, but hey, it works, where it's being read by both the join direct and the shader stages. But the second one is much simpler. It still gets written to from compute, but then it's only going to get read by the join direct stage. Oof. And so this is a little more precise. Than whatever happened before. And I messed it up. Yay! Interesting. For VK image view, what? Hold on. What? Wait, what? This is not even the same. That made no sense. Okay. Pro tip: don't work on Vulkan synchronization at the 3rd hour of the stream. So this was the code before, and I should stash this. This is the code before. What? Okay, so the code before, oh. Nah. So this could be a case where we had this could be two things. So like the problem is, okay, so the problem is we have replaced the barrier that used synchronization 1 with the barrier that uses synchronization 2. The reason why and so this is the code with 1, passes synchronization validation. This is the code with 2, it does not pass synchronization validation. The interesting thing is that we have replaced the barrier that was a buffer barrier, like 2 buffer barriers. And the validation complains that there's a hazard for an image view, which wasn't part of this barrier at all. This could be for 2 reasons. 1, there's like a weird bug in the validation code. 2, maybe this barrier was hiding the lack of synchronization for some image before, or this barrier, due to how the API works. And like now that we use a more precise specification of things that happen, this problem, happens. There's an image with a general layout which must be the pyramid image. It's always the pyramid image. The hazard is right after read. Is it the first? Is it the second frame when we... Wait, where's my assertion? Hold on. Oh, this is cute, actually. Right, so... This is surprising. The fact that there is a missing barrier is less surprising than the fact that the code that used synchronization 1 didn't flag it. Is it the first level? Yeah, it's the first level. And it's on dispatch. Yeah. Yeah, essentially the problem goes like this. This is the stupid problem. Okay, so the pyramid image is being read by the calling stage. What happens on the next frame? It's not even on the... There's again this weird problem with... Okay, so what happens during the calling stage is that the pyramid image gets read. Or as far as the API concerned, it gets read. Actually, it's not getting read in this first pass. We already discussed this, whatever. The API thinks that the image is getting read. Then we render into the pyramid. What technically has to happen is that this is a write. When you read from a resource and then you write to the resource, you have to put a barrier, because if you don't, the theory is the writes could happen while the reads are still outstanding, and they kind of clobber the data that is being read from whatever was there before. So you do need a barrier that transitions the pyramid from the I'm being read stage to I'm being written stage. And this barrier indeed is missing. I don't even know why it says depth read barriers, where there's only one, but there clearly should be one more here, which transitions the pyramid from some reads to the pyramid may have happened before to no, actually we are going to write to this now. The thing that weirds me out is that somehow this wasn't flagged before, but okay. All right, so depth read barriers, sure. It's not even a read. It's so hard to name these things. But and it's being read by the compute stage. I'm gonna bravely attempt to convert this 1 to 2 as well. If this doesn't work, we'll just undo the thing, end the stream, and then there's like more barrier fix up that has to happen. What I'm learning is maybe synchronization 2 is a good idea, because if you use synchronization 1, you just get missing diagnostics from the validation layer. And like it's good to actually fix that, because it's good to make sure that your code is correct. Like, to be clear, everything barrier related we fixed today, we didn't fix because like, oh, validation layer complaints. We fixed it because there is like a bug in the code. And fixing bugs is a good idea generally. Okay, so all right, so we converted the first barrier. The reason why I wanted to convert this is because there's again this problem where there's two different stages, and oh, this had a dependency by region? Is that even correct? I guess it's correct for the depth target. Don't think it's correct for the... So this is the worst remaining, in my opinion. This whole thing is the worst. Oh dear God, what the hell? By region, Control C doesn't work. Oh, it doesn't affect. Okay, it's correct, I think, to include this. Yeah. Well, we are doing a sync with compute, so like it doesn't actually matter. Okay. So, this whole barrier business is like the worst remaining part, I think, of the Vulkan API, because it's the part that's really difficult to get right, as you are observing. And some people swear by the render graph frameworks. But like the problem doesn't get easier. The problem gets easier if you have the framework implementation figures things out for you, but it's like you have to tell the framework about every possible thing that has to happen. Which if you forget that, then the framework doesn't help you. Like, it's not just the fact that you have to establish a dependency between the two resources, which is much easier conceptually. It's the fact that you have to be super precise about what exactly happens with every resource. All right, so depth pyramid in this pass. I don't even know where the barrier for the depth pyramid was before this. It's there here, but it's a different story. Okay, so before this, so after this, the pyramid is gonna be written to, and it's always a general layout. Before this, we actually don't, let's just say it's general, because oh, we can downgrade some stuff. Okay, hold on. So let's just say this is general, but before this, the issue is essentially the issue that the validation layers were complaining about is that the pyramid was being read in the compute shader stage naturally, and now it's being written in the compute shader stage. And the reason why I split these is that, again, the stages are different. So all right, let's see if this fixes the problem, and I dearly hope it does. It does not. Oops, it is not a depth buffer. Please work. No. Now there's a write after read for a buffer. All right, I think the sensible thing would be to undo the couple of changes that triggered this and like do Clearly there's still bugs that need to be fixed. But what is it saying? Hazard right after read. We are writing to, but it's a buffer now. Wonder which one. Storage buffer bound at index 2 in the call stage. Draw commands. Okay. Which we are not synchronizing with. And it's the same problem where it was being read. The draw commands were being read, which they were. It's the same problem basically, sorta, kinda, but in a different stage. The calling says you already used the draw commands buffer to render from them here, because rendering was like using the draw command buffer, and now you're gonna write to this, so you better synchronize stuff. All right, fine. If that doesn't work, then we are done. I mean, we are done regardless. But last thing, it just would be cool to like end on a positive note. Realistically, essentially what has to happen at this point is every single barrier needs to be converted to the pipeline barrier 2, because until you do this, you can't, even once you do this, you can't be sure. But until you do this, you clearly cannot be sure that you actually got everything right. All right, so what were we talking about? The calling code. All right. Had this problem where it's filling 2 buffers, but only has a barrier for 1. And the command buffer, so it's just gonna write to it from the compute shader, but the previous usage of the command buffer is again really funky. It's the same business for rasterization stage, which we should just move like here. Where it was being used definitely as, it was being used both as a draw indirect buffer and during the rasterization stage to read draw ID from it. And because of this, the access is both, it's basically the mirror image of this thing. It's the same thing that we need to specify. All right, please work. Yes, 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 yes. Victory. All right. So we still may have bugs in our code because we haven't converted all the barriers, but we've converted like most barriers. If you search for VKCMD pipeline barrier 1, 2, we converted this one. 3, 4, 5, 6, 7. Okay, so there's still 7 barriers to convert. We are not going to do this now. It's the conversion itself is a very mechanical process. It's just that when the validation layer, as a consequence, discovers a new error that was hidden before, then you don't see that. I'm gonna finish the conversion later today or tomorrow and just push the code on GitHub. So if you watch the GitHub repository, you are going to see the final, hopefully correct code. All right. With this, we have definitely completed the stream objectives and more. It was a little painful. Let me, thankfully there's not a lot in chat, so let's just quickly. Do you often encounter synchronization problems that are not caught by the validation layer and result in actual synchronization bugs? So this is the difficult question about the Vulkan synchronization. In theory, in theory, any bug in synchronization may result in the hardware, in an issue that is visible on a given hardware. In practice, many of them don't. This is for a few reasons. One is that the Vulkan spec requires you to be very precise about this specification, and the hardware is much looser. So the hardware, for example, doesn't actually have resource tracking in a sense. It doesn't actually have a hardware command that says, oh, this resource is being written to on compute shader and it's being read on the graphics shader, so synchronize these two accesses. It's much, 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 much broader than that. Because of this, what the driver does is it takes this very specific specification of barriers and then converts it into a much more general version that is used in hardware. But the version that is used in hardware varies per hardware. So it depends. On some hardware, converting image layouts is the biggest thing that you can observe. And so if you mess that up, you have a problem. But if you mess something else up, it's not a big deal. On some hardware, some synchronization, like compute stage, if you remove a dispatch between a barrier between two dispatches, you might see a problem more easily, whereas if you don't, you might not. I don't know if we can demonstrate this. Do we have a shortcut for the pyramid level that we're rendering? Hold on, let me see. We do. We might be able to demonstrate a barrier that is critical. But so the short answer is, unfortunately, you don't know. And what may happen is you have code with broken barriers that works completely fine on your system, and then somebody else tells you your code has, like, it doesn't render correctly, and you suspect a driver bug, but what actually happens is it's not a driver bug, it's like your code was broken. Let's see if I can show a bug. So this is the depth pyramid, and there's compute shader stages that downsample it. So this is the original image, more or less. I think it's like slightly downsampled. Next. Now you can see the pixels, right? Next. Okay. So we probably will not see the bug because the image is so stable. I can't turn the camera. And the meshes don't rotate. I used to have this code. Oh, but this needs upload on every frame. Meh. So we might not see a bug because the image is stable. Let me try to remove a barrier. I'm running in release now, so validation is disabled, so I can just remove barriers like nobody's business. Let me try to remove it. Where even is it? Pyramid. Oof, I'm tired. So let me try to nuke this one. See if that breaks anything. No, unfortunately it doesn't. The image is stable, this is the problem. Yeah. Anyway, so if the image was actually moving, I think removing this specific barrier would have actually been very visible. And it would result in like flickering of the image or things like that. So yeah, so the flags with 2, it looks like the flags with 1, or like the flags without a suffix, are a subset of the flags with 2. We can try to validate. This might only hold until extensions. Let's try to validate this. So let me do this. Oh no. How do I duplicate the display? All right, I guess I don't duplicate the display. So let's just copy this here, and let's see pipeline stage 2. Copy resolve are new. might actually be able to make some baitters a little more precise now. So let's see. Top of pipe, drawing direct, vertex input, vertex shader, tessellation control. Like they look the same. I don't, there's probably in the spec something that says you can use, these are the same. I think they probably diverge in extensions. So this, for example, I'm not actually sure about. We used it in the mesh shader code, but is it actually correct? Let's see. Eight and 4 zeros. 8 and 4 zeros. They're the same. 1 and 5 zeros. So what I hope happened is that they just upgraded the enum to 64-bit integers, so that all of the existing values map 1-to-1. But if they want to add new values, they now have 32 more stages to fill. You can check the spec. All right. So I think we are done. I am going to commit the code that we have fixed up, and I'm going to try to fix up the rest of the code today or tomorrow and push it to GitHub so that we are completely solid as far as the validation is concerned on synchronization. With that, thank you everyone for tuning in. I don't know when the next stream is going to be or what it's going to be about. We will see. It's probably won't be very soon, but maybe in a month or so, we will see. Subscribe to Twitter if you haven't yet, or follow on Twitter if you haven't been doing that, because I usually post announcements like a few days at least beforehand. All right, with that, thank you everyone, and bye till next time.